Okay, let's continue the discussion with the other sections of the book. Since I'm just running through and not really going into any details, we will probably finish it in this podcast, but it doesn't matter. Need be, we'll do another one. Connecting ocean observations with predictions. Obviously, ocean predictions rely on integrating the models with data from various sources like satellites and in situ and Lagrangian observations, moving satellites, moving buoys, or autonomous gliders, ships, etc., with moored buoys and so on. But now, advantages as satellites offer high-resolution observations of essential ocean variables at the surface, and that's kind of the limitation of the satellites, that they only can observe a little bit of the ocean. Most of the times very close to the surface, sometimes just a few millimeters or so. But they are widely adopted. Their coverage tends to be good, but they are, in situ observations can give you depth profiles, but you cannot have too many of them. Argo profiles fill in the gap a little bit in terms of resolution, but even then they have all kinds of shortcomings as well. And deep ocean Argos are coming along now. Argos can also measure biogeochemical variables and so on. So there is a constant progress in improving the ocean observing systems in terms of their spatial and temporal coverages and the accuracies, bioacoustics, visual data, and machine learning and deep learning methods now allow us to merge the data that are coming at very high speed, varieties of data, and variables that are very different: physical, biogeochemical, audio, visual, and so on and so forth. Okay, so that's basically the idea on obviously, when you want to connect ocean observations with predictions, you have to focus a lot on data assimilation, which we will touch on a little bit. So, moving to merging and serving ocean observations, a description of marine data aggregators. Again, there are various entities that do this, like the Copernicus Marine In Situ Thematic Assembly Center. That's called Marine INS TAC, In Situ Thematic Assembly Center, European Marine Observation and Data Network, the Sea Data Net, and so on and so forth. So idea is to obviously monitoring and managing marine resources, and the paper here discusses the future directions as well for ocean data integration, emphasizing the opportunities offered by the standardization of data dissemination protocols and the role of cost-effective citizen-based data collection. There are various examples of crowdsourcing data, which is obviously much easier on land, but even in the coastal regions, a good example is where the Indo-French effort in the Bay of Bengal was collecting water samples close to the coast with fishermen and people, which monitored salinity, for example. But ships obviously do a lot of data gathering as well over time. Volunteer observing ship network has been very useful, and so on. Okay, data assimilation schemes. So bringing those two sections together into data assimilation schemes. Where are we in terms of the state of the art? Data assimilation is a process for integrating models and observations into comprehensive and reliable estimates of the ocean state. So we either do initialization for predictions, in this case that's the focus, but often we also blend data and models in the past to create gridded, dynamically interpolated data sets like ocean reanalysis, which have allowed tremendous which have given tremendous resources for advancing process understandings and so on. So data assimilation is used to produce near real-time initial conditions, so analysis from which ocean forecasts are produced, and to generate reconstructions of the past state of the ocean, which we call reanalysis, as I just mentioned. Here we provide an overview of the methods currently used in ocean systems for assimilating satellite and in situ observations, together with a brief review of methods being developed which will be implemented in future operational systems, including the use of machine learning techniques that provide a way to improve their efficiency. In terms of the multi-layered structure and variety of sources, AIML are very good at capturing patterns, and also can improve the filling of gaps in the data and so on, better than what we can do generally with just the standard statistical approaches. A list of data assimilation software used by most of the global and regional operational ocean forecasting systems is provided, together with the availability of each software. So we'll just jump ahead and look at that. So there are global data assimilation systems. So US has a few, Canada, EU and UK. So ECMWF is the European Union, and there is also France doing its own thing, Italy doing its own thing, India of course does its own thing, Australia, China has multiple systems, Japan does a lot of data assimilation, ocean prediction, etc. Country like Japan is heavily dependent on the ocean, fishing and transportation. They also have to worry about tsunamis and so earthquakes, tsunamis and so on. And of course lot more centers are now also doing biogeochemistry and not just physics. So you have to there are various details given here in terms of the spatial and temporal resolution. So this is here, for example, Canadian system is only at 25 kilometers, whereas NRL, which is a naval research laboratory, is doing 1/25th of a degree, so that's close to 4 kilometers, and there is a 1/12th coming out of NOAA as well. And there are different methods being used and different variables being assimilated and so on. So just keep those in mind, and if you want further details you can go and read the chapter. It's a very nice long chapter with lots of details and references. What are the numerical models for simulating ocean physics? It's a bit general, but still we know that at an elementary level the spatially varying properties of the ocean that physical ocean models represent, and the principles they use to evolve these properties with time, the physical phenomena that they simulate, and some of the roles of these phenomena played within the Earth system are described in this chapter. And they describe at an intermediate level the governing equations the models use and the grids that they typically use, and at a more advanced technical level the methods and approximations that the models use and the difficulties that limit their accuracy and reliability. And they also briefly describe the wider context and future prospects for the development of these models. I will skip all those details because we have discussed some of it elsewhere, but that's almost a course in itself, learning ocean dynamics, ocean models, the details of the choices one has to make in terms of grids and resolutions, depends on the goal of the model and so on, whether it's regional, whether it's coastal, whether it's global, open ocean, etc., right? And whether it includes biogeochemistry, fisheries, and so on. Numerical models for monitoring and forecasting sea level. Sea level is of specific interest for not only short-term inundation forecasting and fisheries management, but also now worrying about adaptation, longer level variation, sea level rise, etc. Okay, so numerical models for monitoring and forecasting ocean biogeochemistry. So typically the models vary in complexities. So you may have phytoplankton, zooplankton, and bacteria, or just carrying also carbon, nutrients, and oxygen, and whether how many classes or how many size classes or functional groups of phytoplankton and zooplankton you have, whether you have calcifiers and nitrogen fixers and so on and so forth. So lots of details and how they are forced, what exactly they are trying to do, whether they are just trying to produce primary production and carbon psycho exports and so on, or whether they are trying to actually feed into fisheries models and so on. So obviously a lot of times calibrating and parameterizing these models are very tricky because the observational networks are growing for biogeochemistry, but they tend to be very limited in terms of the rate parameters that are needed, various measures of flux, export fluxes, and assimilation rates, light harvesting capacities, and so on. So lots of empirical assumptions are involved. Numerical models for monitoring and forecasting ocean ecosystems. So here we're talking about biogeochemistry. So you are basically doing some lower trophic level ecosystem like phytoplankton, zooplankton, and bacteria, and then focusing on carbon, nutrients, and oxygen. So biogeochemical cycles for carbon, nitrogen, phosphorus, iron, etc. Whereas here you want to do ecosystems. Again, here it may depend on what you mean by ecosystem. Is it actually all the way to fisheries? What is the purpose? Is it supporting marine resource management like fishing, or is it for conservation and marine protected areas, or planning future fisheries, and whether it's for reducing our impact on ocean ecosystems, and so on and so forth. Okay, so individuals, populations, communities, and ecosystems are included. In other words, if you are only trying to track, let's say, dolphins or tuna or some other ecosystem, what are the details you need to do that? Do you need to go all the way from nutrients to phytoplankton and zooplankton to dolphins, including forage fish and intermediate predatory fish, and so on and so forth, etc. Okay, lots of details. I wouldn't be doing any justice by just reading it very briefly anyways, but it's a good chapter. Again, you should go and read it. Numerical models for monitoring, forecasting sea ice. This is becoming important not only for transportation, ship traffic, and fishing, etc., but also for how they affect ocean circulation, water mass formation, sinking of waters, and how water masses are modified, and how air-sea fluxes of heat and carbon are affected by sea ice distributions. And this chapter looks at the overview of how the processes are modeled and how operational systems work in terms of sea ice forecasts. NOAA also does just empirical forecasts, just take satellite data for past sea ice concentrations, let's say, and relate them to winds and circulation in some ways, and explicitly predict winds and circulation, and just do empirically sea ice. Okay, this also gets used quite a bit. Okay, so there are details in this chapter about the data assimilation techniques and discussion on how to enhance accuracy and reliability. Okay, each chapter provides some words on future directions, but I'm obviously skipping all those. This is about an introduction to operational chains in ocean forecasting. So let's just jump ahead and look at a figure. This is from the Chinese system called NMEFC, National Marine Ecosystem Forecast something. Operational chain of an ocean forecasting system. So here you have data processing, data simulation, numerical simulation, and the products. Obviously you have atmospheric forcing, which can include dynamic forcing and thermal forcing, so momentum and fluxes, buoyancy and heat fluxes, and you have observational data in terms of sea surface temperatures, temperature profiles, salinity profiles, and you have hot start. So how to run the models. Hot start field basically means you keep integrating the model and you save it in such detail that you can instantly start from where you left off. World ocean, atmosphere, climatology, runoff data, so rivers have to be worried about. We'll visit that a little bit later on as well. And then it goes into observation reading, error setting, operator calculation, ensemble background error covariance, which is related to data assimilation, iterative solution of ensemble Kalman filtering, which is a data assimilation method that we didn't get into the details, incremental output to the next step, and the model keeps running, and there is the constant iteration between the model and the data in terms of data assimilation, validation, calibration. So product guarantees for oil spill research and rescue, marine engineering, marine fisheries, customized products, and there are websites to provide the visualization and user applications. Depends on how interactive they are. Can users just take what is given on the website, or can they choose various variables they need and change the input to get the output they want? So for example, can they do things? Anyway, let me not go there. Okay, a description of validation processes and techniques. Very important part, but kind of a mundane technical part, so I will almost completely skip it other than mention it. A description of model intercomparison processes and techniques for forecasting. This is very common among modelers. We compare just the ocean circulation models or biogeochemistry models, or we compare ocean forecasts. Comparative projects are very useful. You want to see who's doing well and why, and whether the ensembling of different forecast products will improve the overall skill. And you compare reanalysis products as well, or you provide it to the community and community does the reanalysis intercomparison and so on and so forth. Again, sometimes they tend to dissolve into beauty contests, but usually the idea is to learn how to improve all of them in some ways. Okay, atmospheric driving, atmospheric forcing as a driver. As we said, a lot of times the oceans are forced when they are doing ocean prediction, but we'll see some coupled forecasts in a minute as well. But you need winds, and you need sensible heat in some way, latent heat, long wave, and of course solar radiation. There are often many flux products available, and they may be model products like from numerical weather prediction, because when you do ocean prediction, you need near real-time forcing, whereas all the other fluxes may be computed in the past and not available in the near real time for integrating the model forward. But you need to understand the differences in the fluxes and understand which fluxes have to be interactive. For example, latent heat flux depends on the SST and SST's impact on humidity and wind speeds and so on. So you need to make the flux interactive. You cannot prescribe the flux because atmosphere has a very low memory and time scale is very fast. If you prescribe fluxes, it will act as if ocean has a fast time scale and atmosphere has a slow time scale. So there are all kinds of technical details that we have to worry about when we do ocean forcing with the atmosphere instead of the atmosphere being forced by the ocean. Ocean has high heat capacity, moves slowly, so for several days you can prescribe SSTs that persist without losing much accuracy in the atmospheric response, but you can't do the reverse for the ocean in terms of fixing the atmosphere. Atmosphere has to respond to changing ocean as well rapidly, right? So examples of global atmospheric forcing products. So I won't go into the details, but global forecast system from NCEP in the US, NOAA's lab, NavGem, which is US Navy fleet numerical model, ECMWF and ERA5, so forecast system and the reanalysis products. Depends on what you are doing. So ERA5 is used when you are doing process studies, for example, but if you are doing forecasting, then you may need IFS. Met Office has its own product, GEM. It is from Canada, Canadian system, and so on. Okay, the representation of rivers in operational ocean forecasting. So it's a review, but I won't go into the details because it is still kind of empirical. We don't understand the river coming in at a very fundamental level. We have to make some assumptions. For example, does it come in and go out like a estuarine circulation? What kind of salinity comes in? How does it get mixed? And can you just represent it as rain falling instead of rivers coming in? So all sorts of details are there. And this chapter discusses that in a fair bit of detail that you want to understand. If you want to understand, you have to read it, but basically it's still a very tricky issue. Often we just tune it to get the right answer, but still you may only tune it as a seasonal cycle. In the Bay of Bengal, for example, there is the pre-monsoon season, monsoon season, when the runoff begins to increase, but maximum runoff may happen after the rainy season is over, and so on. So plus, if sediments are coming in, nutrients are coming in, organic matter is coming in, how does it affect light penetration, heat budgets, biogeochemistry, and so on. So, the vertical structure of the ocean critically depends on the details which we don't understand very well. Towards Earth system models, so that is coupled ocean forecasting. Where are we headed with that? Forecasting across different Earth system components has initially been achieved independently, but increasing computer power, increasing model accuracy, increasing connectivity between experts, and increasing need for multi-hazard weather warning is changing the scene in terms of ocean forecasting. Coupling methods which involve exchanging information between discrete modeling systems like the ocean, land, and atmosphere enable us to gain accuracy and consistency across Earth system components, which may include things like river runoff and the impacts on ocean mixing, ocean heat budget, etc., as well as impact to the atmosphere, convection, moving Earth, storm systems, etc. This paper explains the principles of two-way coupling, where models can run simultaneously and exchange information both ways. Main thing to remember is these things tend to be expensive, so making forecasts with these for near real time, if you need 15-minute forecast or even few hours or few days, can be very tricky to run coupled models unless they are regional, but even then resolution can increase computational cost very rapidly if they are coupled. As individual models reach better accuracy, coupling becomes a key factor to improve forecasting capability because it produces the natural complexity of the environment. A wealth of literature shows the benefit of coupling. However, coupling is still limited in operational oceanography by its large demands on computational resources, by data assimilation techniques, also the heavy computing needs, and by administrative separation of forecasts across different Earth system components. Overcoming these barriers will support ocean predictions towards a multi-hazard approach and more accurate representation of the system component interactions, and improve collaborations between multidisciplinary forecasting communities. Obviously, you will have to think about it in global and regional context. So this is a regional coupled system under development in the UK. So you have the atmospheric model, wind and surface drag being exchanged with wave model, because the waves change the surface drag and affect the wind. And you have ocean model NEMO, which is originally a French model. Land surface model is also exchanging fluxes and radiation, temperature, evaporation, precipitation, river runoff, and so on that affect, so surface SST and currents affect the atmosphere, and then it gets wind, pressure, temperature, radiation, and surface fluxes. And of course you have current depths, wave height, distress, dissipation, wave height, stress, and dissipation, not distress, and biogeochemistry, of course. So this is under development, so you will have, actually these papers are old. This book itself is from 2025, very recent, so you have to see what the status of this is. But eventually maybe ML is mixed layer in ocean models, oceanography, so I always keep saying mixed layer instead of ML, machine learning. Okay, so machine learning and AI and deep learning may allow us to do coupled forecasting without having to run coupled dynamic models. This is already happening for weather and climate, and maybe for ocean predictions it will soon be available as well. Improving accuracy and providing uncertainty estimates, ensemble methodologies, and ocean forecasting. So when you do just one simulation, it gives you one realization of the forecast, but Mother Nature can go in many different directions potentially based on slightly different initial conditions that are different from the model, what model is getting when integrating forward. So there is uncertainty in the way the forecast or the state will evolve in the coming hours and days. So doing ensembles by perturbing the initial conditions gives us ways of capturing the uncertainties, and there are many details that I won't go into, but you can see here selected operational ensemble forecasting systems. Just for the sake of some understanding, we'll look at the institutions: Met Office UK, Naval Research Laboratory USA, Bluelink Australia, ECMWF, the European Centre, NERSC Norway, KAUST in Saudi Arabia is doing a lot these days, INCOIS India, of course. I mentioned Bureau of Meteorology in Australia, CMA China, CMCC, that's Italian, I think. So C state from EC, and France always does things as well. Okay, crafting the future, we are getting close, so I will just run through all the chapters and then conclude the podcasts. Crafting the future, machine learning for ocean forecasting. I have discussed this a lot in the climate system, not more specifically for the ocean, but here artificial intelligence and machine learning are accelerating research in Earth system science, which I have discussed elsewhere, with huge potential for impact and challenges in ocean prediction. Such algorithms are being deployed on different aspects of the forecasting workflow with the aim of improving its speed and skill. They include pattern classification and anomaly detection, regression and diagnostics, and state prediction from nowcasting to synoptic, subseasonal and seasonal forecasting, so all days to months. This brief review emphasizes scientific machine learning methods that have the capacity to embed domain knowledge to ensure interpretability through causal explanation, to be robust and reliable, to involve effectively high-dimensional statistical methods supporting multi-scale and multi-physics simulations aimed at improving parameterization, and to drive intelligent automation as well as decision support. An overview of recent numerical developments is discussed, highlighting the importance of fully data-driven ocean models for future expansion of ocean forecasting capabilities. I have a playlist on AI ML in Earth System Science and Climate Science, so I will take this chapter and include some details over there instead of including it just briefly here. Okay, unlocking the power of parallel computing. We mentioned computational costs, obviously, as resolutions of models keep increasing because we want higher and higher local information, higher resolution local information. The computing demand go up, so GPU technologies are becoming more and more common, and of course that also can combine with deep neural networks and machine learning and artificial intelligence, etc. Okay, what are the disadvantages? Graphic processing units offer a rapidly growing and valuable source of computing power, rivaling the traditional CPU-based central processing unit-based machines. The exploitation of thousands of threads can significantly accelerate the execution of many models, ranging from traditional HPC workloads of finite difference, finite volume, and finite element modeling through to the training of deep neural networks used in machine learning and artificial intelligence. Okay, so despite the advantages, GPU usage in ocean forecasting is limited for various reasons, and this chapter discusses it, but I won't go into that. Okay, distributed environment for ocean forecasting. So cloud computing is becoming very useful, and some big corporation like Microsoft or Amazon or Google maintain a big computer, and you don't have to own the infrastructure. You can just rent computing space on it. So this is an overview of existing service models and deployments such as private cloud, public cloud, community cloud, and hybrid cloud, and the series of examples from Weather and Ocean Community are briefly outlined, demonstrating how specific tasks can be mapped and so on. So this is kind of outsourcing, well, not outsourcing, but basically you don't have to invest in massive power and computing systems yourself. You can just buy it buy computing time when you need it. So it works something like this: ocean value chain and associated cloud patterns. So upstream data examples, CP1 is there, satellite buoy, research vessels we saw before. So that's dealing with the upstream data. And there are other processors, cloud computing patterns that are doing the community core service. This is a figure we saw before. We're just adding cloud patterns to it. CP3 to information, immediate users, CP5, 6, and 7 for the multiple downstream data services. There is other data sources also feeding into CP1, and then you are spitting out all your products for end users with customized end user information for policymakers, businesses and practitioners and citizens. Okay, end user applications for ocean forecasting, present status description. So oops, what happened to all my figures? This is yeah, I guess that's all I included. So that's okay. So capacity development, basically about ocean prediction being something that should be made available to all. So process of strengthening the abilities of individuals, institutions and systems to generate, access and understand as well as apply ocean prediction tools and information. You want the entire system to become sustainable, resilient and so on. So you want everybody to be able to use these tools to make proper decisions. So the capacity building encompasses building human capital, enhancing technical skills, improving physical and digital infrastructure, reinforcing governance, fostering collaborative partnerships and networks, ensuring inclusive participation and providing sustained support, both financial and human, to ensure that ocean prediction services are effective, inclusive and sustainable, especially in developing and vulnerable regions. Of course, this is ideal picture under the Decade Collaborative Center, which is itself under the UN. So where the finance and the expertise to be shared will come from is, a detail that's not really discussed here. So there are varied details on ongoing efforts in Africa. It's called Ocean Prediction Enhancement in Regions of Africa, OPRA. So nice acronym. Africa always is a good place to start in terms of pilot efforts to see how well your capacity building is actually working, because Africa desperately needs help in all these matters. Okay, so this is over 30 minutes and I'm still very brief, but that's okay. As I said, the report is freely available online. You want to follow up, and as I said, I will follow up. I will make a couple of podcasts on AIML in ocean predictions in the AIML playlist. Okay, so this will belong in the ocean playlist, I suppose. Okay, there are many playlists under climate science course that you can scan through. Okay, see you.